Okay, hi everyone. This is the first video lesson for Calculus 1. This is going to be a video lesson about limits. Before we start, I'll say that by now you should have already gotten an introduction from me about the syllabus and about the format of the class, so I'm not planning to go over all of that again. But basically, the way this is going to work is that in each of these video lessons, I'm planning to start off with a little introduction like this, where you'll see me, I'll tell you what we're going to talk about. And then in a minute or so, I'm going to switch over to my document camera, which you can't really see right now, but it's just off the side. When I switch to the document camera, you'll see me writing, and hopefully it'll look kind of like I'm writing on a whiteboard. I'm actually writing on a piece of paper on my desk. So you'll see probably more of my hand than my face, but then I'll come back at the end to kind of wrap things up. So, limits. Limits is going to be our first big topic of the semester. I'll tell you that for Calculus 1, I sometimes think of it as there being three big topics, and that would be limits, derivatives, and integrals. So we're just jumping right into our first big topic. This is going to be all about limits. All right, let's go ahead and get started. All right, so what do we mean by limits? Well, before we can get there, I want to introduce this and sort of give us some motivation for why we want to talk about this topic of limits. And I'd like to start by saying, what is calculus? You know, it would be real easy for us to just jump into the math and never really ask ourselves this. But what is calculus? Now, I'll tell you that overall, it's kind of hard to summarize or simplify into a single sentence. Sometimes I see textbooks that describe it as the study of how things change. All right, so that's a quote that I've gotten from a textbook. Is that what calculus is? Well, yeah, in a way. I think that the true answer is that what calculus is going to be gradually revealed to you over the course of the semester. There's no simple way to sum it up in a sentence or two. Um, it's the study of how things change, but it's also a lot of other things. So I'm going to say that it is also the study of limits, continuity, infinity, derivatives, optimization, integrals, and more. All right, so if you don't know some of those words, that's okay. We're going to get there. Now, to start off, let's start off with a question, another question. We know all about functions from previous math classes. I'm going to say, what happens to a function f of x as x changes? I mean, allegedly, calculus is supposed to be the study of how things change. So, you know, if x is a variable, then we know variables are allowed to change, take on different values. So, what if the value of x changes? What happens to f of x? Well, typically, you know, I mean, really, it depends on what is this specific function. What is f of x? But typically, I would say the value of f of x changes too. But how? How does it change? Does it change by a lot? Does it change by a little? Let's look at a specific example. Let's consider the function f of x equals x squared minus 1 over x minus 1. This is just an example function that I like to look at in calculus. Here's a question for you. I'll ask you. What is the domain? Take a minute and think about that. So hopefully while you're thinking about the domain, hopefully you're thinking about the denominator, right? We don't like to have denominators equal to 0. So I really don't want that bottom part to equal 0. Let's say we want denominator not equal to 0. So the domain is... There's a couple of different ways to write it. You know, you've probably seen in a pre-calculus or an algebra, you've seen domain, and you know that there's more than one way to write a set. I'm going to show this to you in two different ways. One of them is, if it's a set, we should be able to use these squiggly set brackets, and we could say that it is the set of all x such that x is not equal to 1. When we write it this way, the brackets indicate that this is a set. The vertical bar is used for the phrase such that. So it's the set of all x values such that x is not equal to 1. So we don't want the denominator to be 0. Or another way to write this set would be as intervals. Think of the number line, think of intervals. You could go from negative infinity to 1, and then skip 1 and capture everything to the right of 1. If we write sets in these two ways, the first one is called set builder notation. And the second way is called interval notation. And they both have their uses. I probably use interval notation more often. But yeah, we don't want x to be 1. In interval notation, that thing that looks like a U is the symbol for union. It means we want this interval and this interval. Now, I'd like to... Here, that was one question. What is the domain? I'd like to ask another question. How about what happens to f of x? We're still talking about this specific function for this example. What happens to this as x gets closer and closer to 1? Now, x is not allowed to equal 1 because that would not be in the domain of this function. We just said that. So I can't just say x equals 1. But what if x is close to 1? What happens to this function when x is close to that problem point? I'm going to set up a little table of values. So x and f of x. And let's investigate this. Let's see what happens. How about we look at... I'll set up the whole left-hand column first. Let's say we try like 0.8, 0.9. Those are pretty close to 1. We can go closer, so let's try 0.99. And then we can't equal 1 exactly, but we could be on the other side. We could be a little bit bigger than 1. So let's try... There's 6 values of x for us to look at. A little scratch work off to the side here. Scratch work. If I do f of 0.8, 0.8 squared minus 1 over 0.8 minus 1. Do we need to do 0.8 squared? I mean, we could do that, and we can, we could figure out what this is that way. But notice, if x does not equal 1, then we could take this function and factor the top. to x plus 1, x minus 1. And we can cancel. Boom, x minus 1. Boom, x minus 1. I'm allowed to cancel that as long as I know that x is not equal to 1. Because we don't want a 0 over 0 situation. But if x is something like 0.8, or x is something like 0.9, or any of these ones on this table, then this thing that I'm crossing out is just going to be a number divided by itself. Number divided by itself is 1, so it just cancels out. So in this case, the function simplifies to just x plus 1. So I don't even really need to do like 0.8 squared, subtract 1, divide by this decimal. I don't have to do any of that. I could just say that when I put in 0.8, these parts cancel. I'm going to get x plus 1. So 0.8 plus 1, 1.8. It's a nice little trick we did there with factoring. Same thing if we put in 0.9, we're going to get x plus 1. So we get 1.9. If I put in 0.99, I'm going to have x plus 1. So 1.99. If I put in 1.01, we're going to get 1.01 plus 1 is 2.01. And then we get 2.1 and 2.2. So this question was phrased kind of an open-ended question, like, what happens to f of x? We let x get really close to 1 in the middle of this table. What's happening to f of x? It looks like f of x is getting really close to 2. 1.99, 2.01. I mean, f of x doesn't equal 2 exactly, but it looks very close. So let's write that. Let's say as x approaches 1, it looks like f of x gets closer and closer to 2. Okay. I mean, x equals 1 is not in the domain, but it's almost like we're finding the value that f would have. It seems like if x were allowed to be 1, f of x is really close to 2, right? Maybe there's something going on in the graph there. We'll talk about that in a minute. All right, the key idea behind this discussion is we want to describe the behavior of a function f of x, not just that function above, but in general, when x is close but not equal to a particular value. And I'm going to give this particular value a name. I'm going to call it C. In the discussion above, we were looking at what happens when x is close but not equal to 1. And this leads us to our first definition of the course. We write, this is going to be our definition for limit, and we have a particular way of writing this thing called a limit. We write lim. Underneath it, x with an arrow pointing to C. F of x equals L. So this is kind of new definition and new notation for us. I'm going to put a big box around it. We write this if we can get f of x arbitrarily close to L by taking x to be sufficiently close to C on either side, but not equal to C. Let me give you a chance to see all that. That is our definition for limit. The part that I put a box around, we would pronounce it, we could say this is the limit of f of x as x approaches C. And it equals L. I'll say that again. This is the limit of f of x as x approaches C. It's telling us what is happening to f of x as x approaches C on either side, but not equal to C. So in that earlier example, let's revisit that. We were given f of x equals this function. And we can say, I'm going to say, based on the table that we had set up, we were kind of looking at what happens when x is close to 1. Maybe a table is not the most precise thing in mathematics. We'd like to come up with some other ways to deal with limits in a more precise way. But for now, we can say the limit of f of x as x approaches 1 is, in fact, equal to 2. So in this example, C is 1 and L is 2, if you're trying to match up that example with the definition of limit. We were letting x approach 1, and it looked like f of x was approaching 2. I want to point something out here. Note, f of 1 is undefined in this case. It might not always work out that way, but in this case, f of 1 is just undefined. It's not in the domain. So even though f of 1 does not exist, the limit as x approaches 1 does exist, and it just equals a small number. It just equals 2. I'll show you another way we could write this. We can also write, if I take this thing I'm pointing at now, this is an equation, right? It has an equal sign. If I take this little equation and I say, what if we rewrite this, but instead of calling it f of x, what if we actually just like put in this expression that f of x is? So I'm going to say that we could write it as lim of this as x approaches 1 is 2. That's just combining the two things we said above into one equation. And I didn't really prove to you that this equals 2. I think that the table of values seemed to suggest that this thing was approaching 2. We saw numbers like 1.99. Later in this section, we'll talk pretty soon about how to know exactly, definitively, that this does equal 2. I think I said something a minute ago out loud about the graph of this function. Let's graph it. Let's try to look at this visually. Do you know what the graph of that function looks like, by the way? X squared minus 1 over x minus... it's a rational function. Back in algebra pre-calc, you probably talked about rational functions at some point. You probably talked about asymptotes, things like that, ways of graphing them. Well, we saw that, I'm just going to pull back the previous page. Remember this thing when we factored and canceled? We saw that this function looked like you could factor the top and cancel this out and just equals x plus 1. So is this the same function as just x plus 1? Here, side note. Our f of x equals this, and what should I call this? I want to give this a different name. I'll call it g of x. Are these the same function? You know, it looked like the f of x we were dealing with, it looked like it simplified to just x plus 1. You can't, factor and cancel, and it looks like you just get x plus 1. So are they just the same function? And then, like, if I wanted to graph f, would I just graph g and say, it's a straight line, x plus 1? The answer is no. The answer is no. They are almost the same function, but they have different domains. F of x, we said the domain earlier. It does not include the number 1. But this second function, g of x equals x plus 1, if I just talked about that as its own function, ordinarily you would think that just looks like a linear function. Domain should be all real numbers. So it almost simplifies to this, but we need to be careful about domain. All right, so I am going to graph f. That was a side note. Let's kind of section that off. Okay, let's draw, how about 1, 2, do about this kind of scale. 1, 2, 3. That should be good. So the graph of f actually turns out to look like x plus 1, except 1 is not in the domain, so we're going to get a hole in the function there. So at some point in pre-calc or algebra, you should have seen not just asymptotes, but also the possibility that a function can have a hole in it. That's what's happening here. All right, so this is the graph of f of x equals x squared minus 1 over x plus 1. So what's happening as x approaches, or as x gets really close to 1? As x gets really close to 1. Well, we could look at the x-axis and look at the 1 that's written here. X is getting really close to 1. So we're in this kind of neighborhood. We're in this kind of part of the graph. Sometimes, sometimes we'll draw little arrows to indicate that we're going to maybe approach 1 from the left. You could also approach 1 from the right. That's kind of what we did with the table. We looked at things like 0.8, 0.9, 0.99. We looked at 1.01, 1.1, 1.2. So we were in this area, right? And then you could say, well, what is happening to the graph? The actual graph is up above, so let's draw like some little dashed lines or something. When x is close to 1, the function is kind of up here near the hole. And the actual value, like the y value that you would get, is over here. And you can tell from this picture that the value of y would be really close to 2. So the idea is the closer x gets to 1, the closer f of x gets to 2. Even though x never exactly equals 1, and f of x never exactly equals 2, we say that the limit equals 2. I'm going to just write write this, I'm going to say as x approaches 1. And I mean from either side, left or right. F of x approaches 2. Now we're talking about this limit where this function has a hole in it here. We could also talk about limits. We could also have ones where there's no hole in the function. But it turns out that in calculus, a lot of the limits we look at are going to be places where there's like a hole in the function or an asymptote or something else weird going on, because those are some of the interesting ones to look at. I just realized that let me fix this. I accidentally wrote a plus sign down here. I don't know if anyone noticed that. I wrote a plus sign down here that should be a minus. I'm going to fix that. That doesn't really change anything about what we said. All right, that's better. All right, let's see. What else do we want to say? Before we move on from this page, I just want to say, looking at the definition of limit, it uses the phrase arbitrarily close to L and sufficiently close to C. And we might talk about those phrases again later in a little bit more detail. Like, what does it mean? What does it mean for two numbers to be close to each other? What does it mean for two numbers to be arbitrarily close to each other or sufficiently close? But for now, we'll just say that the idea is we can make the function value as close to 2 as we would like by taking x to be sufficiently close to 1. Now, we started with a formula for this function, and we've investigated this limit by using a table and by using a graph. What I want to show you next, let's move on from this function. What I want to show you next is that sometimes we are just going to be given a graph instead of being given a formula. And we could have a question about a limit just based on a graph, because this is a very visual idea. So, example, let's say we're given the graph of, we'll call this h of x. New function, h of x, and let me draw this carefully. All right, so we have some weird function like this. By the way, when we draw graphs in this class, we should indicate some numbers on the x-axis and the y-axis to indicate scale. So I put a 1, 2, and a 1, 2. All right, so we're given this. I didn't ask any questions yet. I'll do that here. What is the limit of h of x as x approaches 1? So think about this for a minute. Based on the definition of limit and based on the discussion we've had so far, what do you think this is going to equal? Well, we could do the same thing where we draw little arrows. We could say if x is approaching 1, we're kind of over here, looking at this part of the graph from either side. And then we say, well, really, we want to know what's happening on the graph. Sometimes something that's helpful is instead of drawing the little arrows down on the x-axis, sometimes it's nice to draw them like kind of on the curve itself. Let's do that. You see that? So I'm going to zoom in for just a sec. So what I did was I drew the arrows up here on the curve. Hey, that zooming in works pretty well, doesn't it? Okay, so from the left, we are going up this hill, approaching a hole in the function, but let's just say we're not going to touch that. So we're approaching this height. And if you let x approach 1 from the right, you're kind of going down this hill. Doesn't it look like we're in this sort of height? We're looking at the y value. The function has a y value of around 1. So we'll zoom out. And we say this equals 1. Even though there's this other little point floating around down here. That point's floating around down there at -1. That doesn't really matter to us. We are looking at what is happening to the curve. The curve is very close to a height of 1. I'm going to say note, in this case, it's not G, it's H. H of 1 is defined. H of 1 happens to equal -1 in this particular case. So far we've seen 2 limit examples. The first example we saw was one where the function was not defined at that point, but the limit was. And now we've seen an example where the function is defined at this point, but the limit is different from the function value. So that's something that could happen. Next, we're going to look at one where the limit doesn't exist at all. That's the third possibility. We're going to look at one where the limit doesn't even exist. So I'm kind of spoiling the answer for you, but that's okay. This one's going to be a piecewise function, and we're going to be given a formula for it. Piecewise function with 2 rules. It's going to be x squared if x is less than or equal to 0, and it's going to be 3 minus x if x is greater than 0. Haven't really asked you a question yet, but I'm going to draw a picture of this. I think that you could draw a picture of this yourself if you needed to. This function is simple enough. Anyway, 1, 2, 3, 4, 5. We'll do this kind of scale. At this point in the course, I wouldn't ask you to graph a super complicated function, but you know, x squared is a parabola. Like we're saying that if x is less than or equal to 0, then x squared is just the classic parabola that touches the origin. So it's going to go here, here, and here. We'll probably draw this parabola tons of times this semester. But right now we only need the left half of this parabola because f of x equals that only when x is less than or equal to 0. And then when x is positive, when x is greater than 0, 3 minus x. Do you know how to draw that? It's a straight line. You could rearrange it, flip it around so that it's like y equals mx plus b. The slope is -1. The y-intercept is 3. If there were a y-intercept, it would be 3. Notice that this says if x is greater than 0. So instead of having a dot, like we already have a dot here at the origin, I can't put another dot above it, but I could put an open circle above it. That's where the y-intercept would be if there were one. And now slope of -1 means for every 1 unit you go to the right, you go 1 unit down. So that's going to look something like this. So, what question do you think I'm going to ask about this? There is kind of a natural question that is sort of the most interesting limit that I could ask about for this function, and that is, what is the limit of this function as x approaches 0? That's the most interesting part of this function, because that's where the piecewise function switches from one rule to the other. So let's talk about this together. All right, I zoomed in, so we kind of, there we go. I'm trying not to lose too much on the edge of the screen. Now we want x to approach 0. 0 is right here, and we want x to approach that from either side, meaning from the left and from the right. I said sometimes we draw little arrows. The arrows are just a little bit of scratch work, but I'm going to draw them anyway. If we approach from the left, we're on this part of the curve, and we're going lower and lower and lower. But if we approach from the right, then we're on this part, and we're approaching 0 from the right, and we're going kind of uphill, like that. All right, I'm going to zoom out again. So the arrows aren't really touching each other. They're not really going in the same place, are they? When I approach from the left, I feel like the curve is going towards a height of 0. So does the limit equal 0? I think that's a question mark. Let's talk about, what about the other direction? What about when I approach from the right? When I do that, I'm going uphill, 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 and I feel like I'm approaching a height of 3. So maybe that's the answer. Does this limit equal 3? Because if I approach from the left, it looks like it goes to 0, but if I approach from the right, it looks like it goes to 3. Well, technically, the limit definition says we need to be able to approach some number L, capital L, and we need to be able to approach that on either side. The fact that we're getting two different things here means the answer is no to both of these. And we say the limit does not exist in this case. So we're not getting the same thing on either side. And I kind of ruined that for you at the beginning by saying this was going to be an example where the limit doesn't exist. Well, this is sort of how that happens. Happens sometimes with piecewise functions. Maybe it could happen with other functions too. But yeah, something weird was happening there. Now you might look at this and you might say, all right, well, this limit did not equal 0 and this limit did not equal 3. But it feels like that 0 had some significance, and that 3 had some significance. It was almost like that was half of the answer or half of the limit, right? Like if you just approach from one direction, shouldn't that 0 and that 3 still have some significance to us? And it does. We have a name for those, and they are going to be called one-sided limits. So we have two little definitions here. We need a slightly different way of writing them, but it's going to be kind of like a limit, but where you only approach from the left, or like a limit, but where you only approach from the right. There's one little change to how we write it. Instead of writing x with an arrow pointing to C, we write x with an arrow pointing to C, and then we put a little minus sign above it. The minus sign is kind of above the C, almost like it's an exponent. It's like C raised to the minus sign. That's what it looks like. We write this if we can get f of x arbitrarily close to L by taking x sufficiently close to C and x less than C. This doesn't say anything about being on either side. In fact, this specifically says x is less than c, so x is on the left side of c. We might sometimes call that a left-hand limit. We're approaching from the left. And then we also need a definition for the right version, and it's almost the same thing. So I'm not going to write every word. I'm going to say similarly. What do you think is going to be different about how we write this? Well, instead of a minus sign, it's going to be a plus sign. That seems reasonable. There's a minus version and a plus version. One is on the left, one's on the right. And we write this if, I'm just going to put quotation marks because most of this definition is exactly the same. Okay, arbitrary closed L, so blah, 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 blah. And x greater than c. That's the only part that's different. I'm going to underline the x less than c and the x greater than c. Maybe we'll put a box around these things. How about that? We write that, and we write that. There we go. Nice and neat. So that 0 and that 3 that we got earlier, they do have some significance. In the above example, we could say that the limit of f of x as x approaches 0 with the little minus sign next to it, that equals 0. And the limit of f of x as x approaches 0 with the little plus sign next to it, the right-hand limit, that does equal 3. Even though overall we say that the limit does not exist. That's still true. The one-sided limits are 0 and 3. All right, so hi again. It's me again. So how are we doing so far? Is everybody hanging in there? So right now, I would say we're probably at about the halfway point of this lesson on limits. And I thought maybe now would be a good time to just take a quick breather, take a quick break. Of course, on these pre-recorded videos, you're always able to pause them and come back to them. And if you need a break, now's probably a good spot to do that. But so what have we done so far, and what are we going to do next? So far in this video, we have introduced the concept of a limit. It's where we're basically looking at what's happening to a function value as we get really close to something. And we're really looking at kind of the y-coordinate. How high or low is the function approaching? And we started by maybe looking at it in terms of a table, and then we started talking about it in terms of a graph. And towards the end, just now, we talked a little bit about the one-sided version of limits. Now, what we still need to do, and what we're going to be doing next, is we're going to establish some rules or properties about limits that are going to help us to evaluate them without needing a table, without needing a graph. Something that we can do with formulas, something that's going to be more precise and get us the exact answer. So that's coming up next. All right, so I guess let's keep going, and we'll be able to solve some more problems once we get these properties written down. So let's go ahead and start a new sheet of paper. Move that away. So we're still in the section about limits, but now we're going to talk about properties of limits. And we're going to have a big list of properties. We're going to start by saying, suppose C, K, and N are constants. That way we can use them in this list. where n is a positive integer. Also, suppose the limit of f of x as x approaches c and the limit of g of x as x approaches c both exist. You know, we've already seen that it's possible sometimes for a limit to not exist. We're going to suppose both of these do exist. Then, all right, now we can get a big list of properties going. All right, number one. The limit as x approaches c of k, just k. Well, up above it says k is a constant. So what is happening to k, the constant k? What's happening to the constant k as x approaches c on either side? Well, the answer is k is just going to be k. So that's our first property. That could help us simplify things if we ever have a limit that looks like this. If it's like, what's the limit of 5 as x approaches 2? Answer, 5. Because 5 doesn't change just because x is changing. All right, that's our first property. Next one, what's the limit of x as x approaches c? Now that's a little different now. Instead of having a constant there, x is a variable. In fact, we know x is changing. I'm going to say, as x approaches c, x becomes c. It seems reasonable, right? X is going towards c. So what's happening to the limit of x? It's going to c. Next property is going to involve this f of x and g of x that we wrote above. So this is going to be the limit of f of x plus g of x. And the property says that we can split this up into the limit of f of x plus the limit of g of x. Similarly, we have a property like that for subtraction. And I kind of feel like we could have just combined these into one property, but we're listing them separately. So whether it's a plus sign or a minus sign, either way, you can split up those, you know, that the left-hand side was a limit, and you can split it up into the right-hand side, which has two limits. So that could be useful to have later. Number 5. I'll tell you right now that I think there are going to be 9 of these. All right, number 5. Limit as x approaches c of k times f of x. K is a constant. F is a function. This rule is going to tell us that you can take k and pull it outside. Pull it out of the limit. It's almost like taking a constant and pulling it out of parentheses. We're pulling it out of the limit. By the way, you know, an equal sign is a two-way street. You know, if it works one way, it also works the other way. So I'm saying that if there's a k on the inside, that you could pull it out, but maybe you could also think of it the other way around. Like maybe there's a k on the outside and you want to move it in. So it's also a way that this works. Rule 6 is going to kind of look like rules 3 and 4. Rules 3 and 4 were for when you have a limit of two functions added together. or a function subtracted from another function. Rule 6 is going to be for when you have a function times another function. And it's going to say that it is okay to split it up. The limit of the first piece times the limit of the second piece. So limits of sums, differences, products, they can all be split up. Feels like there's one missing. What about if we do sums, differences, products? What about quotients? That's going to be rule 7. It says the limit as x goes to c of f of x over g of x. What would it look like to split that up? The right-hand side's going to have two limits. It says you get the limit as x goes to c of f of x over the limit as x goes to c of g of x. If you want to do this splitting up, then you can. There is one little disclaimer that we need to write next to this. This rule works if the denominator is not 0. Okay? Said we were going to have 9 rules, so we're almost done. Property number 8 is about square roots and other roots. It's going to say the limit of the nth root of f of x equals the nth root of the limit of f of x. So it's basically saying that if you have any kind of root, square root, cube root, fourth root, fifth root, that you can basically pull the root out. You can pull the radical symbol out of the limit. Square roots are probably the most common. Square roots are where we'll probably do this the most often. But you never know. We might see a cube root or something like that. And finally, rule number 9. Rule number 8 and 9 kind of go together. This is going to say, I think they go together. This is if we have a limit of a function raised to the n, that's the same as limit of the function in the parentheses, then being raised to the n. So you can raise to the n first, or you can raise to the n on the outside, and either way, they equal the same thing. So I hope that what you're seeing, like, I don't want you to be overwhelmed that we just wrote a full page of things, like a full page of formulas. It's not about strictly like memorizing all of these rules. I wouldn't really think of it that way. You can notice patterns. You can notice that rules 3 and 4 are saying when you have a limit of a sum, you can split it up. You have a limit of a difference, you can split it up. How about this? Limit of a product, split it up. Limit of a quotient, split it up. Limit with a radical symbol, pull it out. Limit with a power, pull it out. What else? Limit with a constant out front, pull it out. So, you know, most of these are just telling us that limits behave really nicely, and in a lot of ways, I think that they kind of behave the way that we would expect them to. You can break them apart, put them together, pull constants out, things like that. Now, where this big list of properties is going to help us is we can start to solve some limit problems by hand without having to draw a picture of a function, without having to make a table. So I'll show you an example. Let's find the limit of x squared plus 3x as x goes to 2. And we're going to do this without drawing the picture. So since this is the first time that we're doing a problem like this, I'm going to show a lot of steps, but then like as we do more of these, we'll show less and less as we get used to it. I want to think about how these properties could help us. The limit as x goes to 2 of x squared plus 3x. One thing that stands out to me is property 3, because this is something plus something. So by property 3, we should be allowed to split this up into the limit of the first part plus the limit of the second part. I'm going to write off to the side that that was by property 3. It's kind of like taking a problem and splitting it up into two smaller ones. I'm hoping to get like a number for my final answer. We'll see what happens. All right, limit x goes to 2. Let's look at just this first part. Limit of x goes to 2 of x squared. What about property 9? Property 9 was the one that dealt with powers, and it says you could pull the exponent out. Let's try that. If you pull the exponent out of this, it would look like the limit of just x, and then the squared is now on the outside. So that helps. That's going to help with that part. What about the 3x? 3x looks to me like property 5. Property 5 is the one that has a constant and says you can pull the constant out. So I'm going to do that. I'm going to say that this was all by properties 9 and 5. Okay, what is this thing in parentheses? Limit of x as x goes to 2. We have a property that looks like that, don't we? That looks like property 2. Property 2 specifically is for limit of just x. And it says as x goes to 2, this limit is going to go to 2. And then over here, we have 3 times the same thing. This is also going to be 2. So I'll say that this comes from property 2. I told you I was hoping to get a number for our final answer. We just got 2 squared plus 3 times 2, so this equals 10. And that is the answer. So pretty cool. We used a combination of properties. We figured out this limit. So I guess if you were to graph this function, x squared plus 3x, you know, that would be some kind of parabola, because it's quadratic. And then if you looked at what's happening as x approaches 2 from either side, the height of the function, like the y-coordinate of the function, would be approaching 10. Now, you might notice something for this problem is, for this problem, it kind of looks like we could have just plugged in 2. What if we had just taken this x squared plus 3x and we just plugged in 2? We would get 10. In fact, we would get this previous line. We would get 2 squared plus 3 times 2. So is it okay to do that? Like, is it okay to just say, why don't we just plug in 2? It looks like it would get the same answer. Although I think I remember some functions earlier in this video where maybe that would not be okay, like things that were not in the domain, so you couldn't just plug in C. Okay, so the answer to it is it okay to just plug in 2 and skip all these steps? The answer is it depends on what type of function it is. We have a theorem that's going to tell us 2 cases where it is okay to just plug in the number. And the first case is if f is a polynomial. if f is a polynomial, then the limit of f of x as x approaches c is just f of c. In other words, it is okay to just put in c. There's going to be a part 2 to this theorem. And some of you might be saying, well, all right, well, why didn't we just do that in the first place? This seems like a big shortcut. You know, it's saying you have a polynomial, you can just plug in 2. We could have just gotten 10 that way. The reason why I wanted to do this problem and break it all up and use property 3 and 9 and 5 and 2, the reason I wanted to do all this is because that is basically the reasoning of why this theorem is true. The reason that this theorem, the reason why this rule exists for polynomials is because polynomials can always be broken up and solved using these properties 9, 5, 3, 2, property 4. So we just establish it as a rule. And from now on, we can use that as a shortcut. The second part is going to be if f is a rational function and c is in the domain of f, then the limit of f of x as x approaches c equals f of c. And I will remind you what a rational function looks like. A rational function, briefly, is a polynomial divided by some other polynomial. So that's a two-part theorem telling us two types of functions where it's okay to just substitute in c in place of x and bypass all these other steps. For part 2 of the theorem, there's the extra requirement that this only works if c is in the domain. We don't really have to worry about that for part 1 because for polynomials, the domain is all real numbers. I'll show you an example of using this theorem. Let's say we are told to find the limit as x goes to 2 of x cubed minus 1 over x squared minus 1. Now, we could break this down into using all of those properties. I think we would probably start with property 7 and then go from there, see where it leads us. But we don't have to. We can use this theorem as a shortcut. I'm going to say that this is a rational function. It's definitely a polynomial over a polynomial. And x equals 2 is in the domain. How do I know that? I just took a quick look at the denominator and like in my head I figured out what the domain is. But basically, if I put 2 in, are we going to have any problem with that denominator? No, not really. So, the limit of this function, as x goes to 2, is just whatever you get by plugging in 2 for x. Plugging in 2 in place of x. So up top, we get 2 cubed minus 1. On the bottom, we get 2 squared minus 1. Simplifies to 7 over 3. Now this right here is probably the easiest type of limit problem. All you had to do was look at it and say the theorem works and it's in the domain, and you know, we just kind of took this expression and plugged in 2. So because this is the easiest type of limit problem, it probably means you're not going to see a lot of these. But occasionally you will. Occasionally you see a problem like this, and then you're like, hey, that's great. I can just plug in the number. Because that function might have asymptotes or holes in the function or something, but it doesn't have any of those things happening at x equals 2. All right, let's look at some harder problems. The problems, you know, just like any math class, they're going to gradually get tougher. And I'm going to say, note, we might need algebra steps before using limit properties. And the example that I want to show you is actually an example that we looked at the beginning of this lesson, the beginning of this video, was evaluate x squared minus 1 over x minus 1 as x goes to 1. This is the one that we looked at using a table. We did a table of values. We also looked a little bit at the graph. And based on the table and based on the graph, we said that this equals 2. Or maybe I said that this equals 2. But I don't know if we fully justified that. So now let's go back and revisit it, and we'll show that this actually does equal 2. Let me tell you that this function is rational, but c equals 1 is not in the domain. So this is not one of those super easy problems where you just plug in 1. Right? We can't just plug in 1. What would we get if we did? If we plugged in 1, we'd get 0 over 0. And that might seem to suggest to you like that maybe this is undefined. Maybe there's no answer. 0 over 0. However, I told you earlier that the answer is 2. So how can we get 2 out of this? Well, we can factor. Factor, because I said we might need algebra steps. What's the most famous algebra step? It's probably factoring. Everybody's favorite algebra step, right? Factoring. Yeah, factor the top, factor the bottom if you need to, but the bottom doesn't really need anything. We do that because it's okay to cross out the x minus 1 over x minus 1. Earlier I said something about how it's okay to cancel these as long as x is not equal to 1. Okay? Because as long as x is not equal to 1, we just have some non-zero number divided by itself. Number divided by itself cancels, just gives us a 1. Now we know from the definition of limit that in this case, x is approaching 1 on either side, but not equal to 1. So it is okay to cancel, meaning that this limit equals this limit. And now, this right here is just a polynomial. And the theorem says that once you get to a polynomial, it's okay to just put in that x value. Put in x equals 1. So from that, we can just put in x equals 1. And that is how I got an answer of 2 earlier. I think I was telling you that the table of values, the table seemed to suggest that the answer was probably 2. But this is how we know that the answer is exactly 2. All right, so that's one type of limit problem that you might see, something that might need some factoring. You know, I said algebra steps, but might need some factoring, some canceling, and then once you get it down to just being a polynomial, then it's okay to just put in the number. Let's look at another one. Might be some other algebra steps. Sometimes you notice I've been using the word evaluate, and sometimes I've been like using the word find. Another word you might see is compute. It all means the same thing to us. In this one, the letter is going to be called h. We're going to compute the limit as h goes to 0 of 4 plus h squared minus 16 over h. I'll talk us through this one. This is still pretty new for us. A little bit later, I'll have a couple for you to just try on your own. Now, can I just throw 0 in? Like, can I just throw 0 in place of h? I mean, first of all, that would give me a 0 over 0. But second of all, no, I should not just plug in h equals 0, because I have no reason to believe that I'm allowed to do that. You know, that theorem said something about rational functions. This is a rational function, but 0 is not in the domain. So it's not one of those easy problems where you can just plug in 0. So what do? It means we might need algebra steps. So what algebra steps could we do here? Could we do factoring? I think this time, instead of factoring, let's do the opposite and let's expand. Because this little piece up here is already factored. Let's see what happens if we like distribute and expand. So 4 plus h squared, that's going to be 16 plus 8h plus h squared. We expanded. It's another type of algebra step. The nice thing about that is after expanding, I see that I have a 16 minus 16. So let's cross them out. Let's see what that equals. Notice that as I do these problems, I'm starting the next step here. Notice that each time I do this, I'm writing equals limit h goes to 0 of something. Basically, what I'm getting at is when you do problems like this, I want to see equal signs between things that are equal, and I want to see limit of something that is a limit. Okay, so like in the previous problem, I wrote equals limit x goes to 1, equals limit x goes to 1, equals. And towards the final steps of the problem, I didn't have to write limit anymore because we had already evaluated the limit. But yes, you should be writing equal signs between things that are equal. I will take points off. You know, we want you to be writing things on the page that are true, and we want to be able to follow your work. So just keep that in mind. Let's see. Let's pull out h from what's up top. Boom. How about that? Factor down h from what's up top, because I saw an 8h and an h squared, and I saw that if I do that, that's going to work out nicely because I'm going to have h over h. H over h cancels out. Giving me the limit as h goes to 0 of 8 plus h. This piece, kind of like in the previous problem, this piece is a polynomial. It might not be a polynomial like you're used to, because, you know, typically polynomials, we're used to the variable being called x. This time the variable is called h, but it's just a different letter. It's just a different label. It's still a polynomial. And at this point, it is okay. The theorem says that once you have a polynomial, it's okay to just plug in that value. So we're going to get 8 plus 0, which is 8. So I think in a problem like this, we couldn't really tell, like, just looking at the original problem, we couldn't really tell that that was going to equal 8. For a brief moment, it almost looked like this was going to be undefined, like a 0 over 0 type of situation. But yeah, it does in fact equal 8. We got there by doing some algebra and then applying that theorem. I've got another one for you. This one is going to also use some algebra steps, and it's another type of algebra step that you might need. So the limit as x goes to 0 of the square root of 1 plus x minus 1 over x. Let's talk about this together. All right, first things first. Does the theorem apply in any way? No, the theorem doesn't apply because this is not a polynomial. Also, this is not a rational function. Rational function would need a polynomial up top and a polynomial on the bottom. This square root kind of throws everything off and just makes this a unique kind of problem. I'm going to tell you off to the side a trick that helps us with problems that look like this. So when we are given an expression of the form square root of a minus square root of b, the conjugate is square root of a plus square root of b, and vice versa. An algebra trick. This is actually something that could be used as an algebra trick in previous classes, in like an algebra course or pre-calculus. We're using it here in a calculus problem, but it is really just an algebra trick. We are going to multiply this problem by the conjugate over the conjugate. And we're going to see that that helps simplify things for problems of this type. For problems where you've got a square root, you've got a numerator, and you've got a denominator. Okay, so let's copy the problem, but leave ourselves a little bit of room for multiplying stuff. All right, I am going to multiply that expression by, what would the conjugate be? Is this even in that form, square root of a minus square root of b? Well, yeah, it is, because you could think of 1 as like the square root of 1. So it is in this form, and the conjugate would look like this, but with a plus sign. So I'm going to multiply by the conjugate, which has a plus sign, over the conjugate. So two things. First of all, are we allowed to do this? And second of all, does this actually make things simpler? Okay, first question, are we allowed to do this? Yes, we are allowed to do this because we are essentially just multiplying the problem by 1, because we're multiplying it by something over itself. So it's like multiplying the problem by 5 over 5. You know, technically, yes, we are allowed to do this. Second thing, though, does this actually make the problem simpler? Because it looks to me like it made it more complicated. Well, the answer is it's going to make things simpler 1 or 2 steps from now. So we just have to bear with me, and it will make things simpler. We are going to do a little bit of distributing. We're going to distribute everything that's up top. We can make this one fraction instead of a fraction times a fraction. Let's distribute. So we've got like square root of 1 plus x times square root of 1 plus x plus, each piece, work it out. The square root of 1 plus x times itself is 1 plus x. And then I guess we have plus this minus this minus 1. All right, so that is the entire numerator expanded. For the denominator, I am actually going to not distribute, not expand. Let's leave it the way it is. It's going to work out nicer this way. The algebra will work out better. Now I've got some stuff up top that I can cross out. Cross it out, same thing. The number minus itself. Oh, you know what else? Look at that. We have a 1 minus 1. Let's cross those out. 1 minus 1. What did I not cross out? Up top, I crossed out a lot of stuff. The only thing I didn't cross out up top was an x. So let's say we have x. Hopefully you're starting to see why this whole conjugate business is going to help us. Because now we have x over x, and we're allowed to cancel those. Just remember, when you cancel x over x, that's going to equal 1, not 0. You know, a number divided by itself cancels and gives us 1 up top. And on the bottom, we've got all of this. We did all that work to get here. Is this simpler than how the problem originally started? I would say yes, a little bit. Because there's 1 fewer x to worry about. From here, let's start applying some of those limit properties. And we don't necessarily have to say property 7 and whatever. Like, you don't have to number what property you're using. But I'm going to use the property that says we can do the limit of the top, the limit of the bottom, running out of room on my page. We'll see if we could fit this here. So up top, the limit of 1 as x goes to 0. Remember, 1 is just a constant. I think that might have been property number 1 that says when you have a constant, that's just going to equal 1. On the bottom, we have some limit properties that say we could split this up into the limit of the first piece plus the limit of the second piece. We also have a property that says you could pull the square root symbol out. I'm going to apply two rules at the same time here. I'm going to pull the square root out. And I'm also splitting up the limit. This 1 here is going to be the limit of 1 as x goes to 0. That's just going to be 1. Do you see that this 1 plus x, just the 1 plus x part of it, not the rest, but this 1 plus x part of it is a polynomial. So deep buried within this problem is a small polynomial, and we like that because the theorem tells us that for this little piece, we could just plug in x equals 0. So this will just be 1 plus 0. So square root of 1 plus 0. Square root of 1 plus 0 is the square root of 1. The square root of 1 is 1. So I think what I have then is 1 over 1 plus 1. My answer is 1 over 2. Okay, so that was probably the trickiest problem that we've seen so far. The square roots and the conjugates make it a little trickier. The 3 problems that we just did, all of them are types of problems that you might see, and they involve a little bit of algebra and limit properties or the limit theorem. You know, you might need to do factoring, you might need to do expanding, you might need to do conjugate over conjugate, depending on what type of problem it is. So next, I have some problems that I'd like you to try, and you'll get to see me do them also. So I'm going to give you 3 problems. And in these, pre-recorded videos that you're watching, basically if we were doing this in person, I could give you some problems and then I'd give you a few minutes. Maybe I would walk around the classroom and see how it's going, help out, stuff like that. But because it's a pre-recorded video, what I'm going to do is I'm going to write 3 problems. So wait until I've written all 3 of them. But I would encourage you to then pause the video and give these problems a try. And then you can hit play and you'll see me talk about them, go over the solutions. All right, there's part A. A big part of math is doing math yourself. I don't think you can really master calculus just by watching me do it. You need to be working on problems yourself. Sometimes you might need to struggle a little bit. You might get stuck a little bit. That's all part of the process. It's all part of the learning process. Try to struggle through it. Try to learn from your mistakes. And yeah, we'll get there. You'll get where you need to get. All right, so there's 3 problems, and I'm going to encourage you to pause the video here and give these a try. Okay, so hopefully you tried those. Let's talk about them a bit. So, part A. Let's write the problem again. Limit x goes to 1 of x squared plus x minus 2 over x squared minus x. I guess this is a rational function because it's a polynomial over a polynomial, but I think that 1 is not in the domain because if I try to put in a 1, I'm going to have a 0 in the denominator. So I can't just plug in 1. So I'm thinking that we need to do some algebra steps. And the algebra step that stands out to me is we can probably do some factoring. Let's try to factor the top and the bottom. The top factors to x minus 1, x plus 2. The bottom factors to x times x minus 1. The reason factoring is going to help us is because we can cancel x minus 1 over itself. And that leaves us with x plus 2 up top and x on the bottom. Off to the side, I'm just going to try to indicate that this thing here, this is a rational function, and x equals 1 is in the domain. X equals 1 was not in the domain of the original problem, but it is in the domain of this reduced problem. So now it is okay to just plug in 1. Everywhere that you see an x, replace it with a 1, and I get an answer of 3. Okay, so that's what you should get for part A. Part B has a square root, so I don't know. Let's see what happens. Square root, there's a negative 2. All right, 4x squared minus 3. Well, I think the theorem doesn't really apply here. It's not a polynomial or a rational function. Let's just try to use limit rules, limit properties, because we've got that property that says you can pull the square root symbol out. So let's do that. I'm going to do parentheses here. Those parentheses were not in the original problem, but I'm adding parentheses to make sure that the 4x squared and the minus 3 stay together as one piece. We want the limit of that whole thing. You know what I'm going to say? This is a polynomial. This part of the problem is a polynomial. So for that part, limit of this polynomial, you can actually just put in the minus 2. So put in the negative 2 and get 4 times negative 2 squared minus 3 square root over that whole thing. Negative 2 squared is 4, so this is 4 times 4, which is 16. Answer is going to be the square root of 13. And one more to go. Part C. This one is limit x goes to 0, square root 4 plus x minus 2 over x. I feel like this one looks like that problem we did a few minutes ago where the answer was 1/2. I think it's one of those where we want to get the conjugate involved. So I'm going to go ahead and do that right away. I'm going to multiply this by the square root of 4 plus x plus 2 over itself. Right? So essentially, we're essentially just multiplying the problem by 1. And then kind of like that previous problem, we are going to distribute, expand what's up top. Square root of 4 plus x times square root of 4 plus x. All right, 4 plus x. You should get 4 plus x minus 4 as your new numerator. And the denominator, just like last time, I'm going to leave in this form. Next, let's get rid of the 4 minus 4. So I guess in these problems where the conjugate gets involved, it's one of those algebra things where it looks like it's getting more complicated, but then over the next couple of steps, it gets simpler. Sometimes you have to make something messier in order to simplify it. X over x, let's simplify it. X over x is 1 up top. Okay, that's where we're at now. We're almost finished. I want to show you something. I'm going to compare this to the previous one that was like this. All right, when we did this problem a few minutes earlier, you know, this is kind of mirroring the same types of steps. We had this like 1 up top, square root of the stuff on the bottom. That's kind of the step that we're at. It's kind of like this. And in the previous problem, I said, let's start using limit properties. I broke it up. Limit of the top, limit of the bottom, limit of, pull out the square root, all of that. Ultimately, we got 1/2. What I want to tell you for this problem that we're working on now is it's okay if you want to skip writing some of these limit properties. I can tell that the limit properties are going to apply. From this point onward, I can tell that we could do the limit of the top, we could do the limit of the 2, the limit of the square root, pull out the square root. Like, I can see how it's all going to work out. It's going to work out to be this. And there's no limit as x goes to 0 right now, because I got rid of that limit. I'm saying that the numerator is going to be 1. The 2 is going to be 2. The square root of 4 plus x is going to become the square root of 4 plus 0. Because I could see that that's going to happen, it's okay to just skip to this. And now we have, I guess, 1 over 2 plus 2. Final answer is 1 over 4. It's kind of like that previous problem where the answer was 1 over 2. I'll just give you another moment in case you're writing that down, and then we'll kind of wrap this up. We'll wrap this up soon. Okay, so we made it to the end of the lesson on limits. I know this has been kind of a long lesson. Uh, yeah, we're starting the semester off with kind of a big lesson, but we did a lot of problems. We used algebra and we used limit properties to answer some of these. And I'll tell you that what's coming up soon, what's coming up in the next videos is the next one will probably be shorter than this because it's going to be a section on one-sided limits. And the reason why that's going to be a short section is because we already talked about one-sided limits briefly in this one. So we don't have to talk about it too much next time. And then we have some other stuff coming up in the rest of this chapter. There's going to be a section on a topic called continuity, and that's very closely related to limits. And then I'm getting ahead of myself, but the video after that is going to be about limits involving infinity. So whole chapter is about limits. This lesson today covered a lot of it. All right, so that is going to be it for now. And I'll say take care, and I will see you next time.